Welcome to 5G Technology World. I'm Site Editor Martin Rowe. NI, formerly known as National Instruments, has been involved with 5G for quite a few years. They were one of the companies that developed early testing equipment used for channel sounding, particularly in the millimeter wave frequencies. Today, the company has moved more into production test of semiconductor devices for 5G and for other wireless technologies. Today we spoke with David Hall, who told us about a recent agreement that NI has come to with ETA Wireless for testing their new wireless ICs. So David is going to tell us about that and give us an update on 5G in general and some of the problems that engineers currently face in developing new 5G products. So David Hall from NI, I have to say NI now. I have to get used
That's
to
right.
that.
I do too.
So yeah, I think we all do to an extent. So you're heavily involved in 5G. What is National Instruments doing with 5G? And I know that the company has been involved with 5G for a long time, going back to some of the initial channel sounding research that was done. It's got to be 5 years now. So what is NI doing with 5G today?
Yeah, that's a good question. So you're right in kind of the allusion to some of the early work was really on the research side. So, if you look back 5 and 10 years ago, we saw researchers trying to prove that, 5G and millimeter wave communication was even possible at all. That was the work to, do channel sounding at 28 gigahertz, and they were testing at 72 and 74 gigahertz. People were testing out massive MIMO ideas, and that was a long time ago. Now we're in the phase with 5G. It's really in the prime time of deployment. So you look at the sub-6 gigahertz spectrum that's getting deployed globally right now in quite haste. There's a pretty massive deployments happening in China and the US and parts of Europe. And so our primary involvement in that is really in the manufacturing side. So obviously we sell a lot of test equipment into the lab for people developing semiconductor products, but we're also heavily involved in manufacturing semiconductor devices for 5G. And that's true both for sub-6 gigahertz and millimeter wave.
What kind of devices?
So it's a big mix. So if you look at the design of the radio for sub-6 gigahertz, you've got the PAs, the LNAs, the front-end modules, and that's true for both the handset and the infrastructure side. And then those are typically, massive MIMO PAs or even discrete filters, diplexers, those types of products. And then at millimeter wave, there's actually a couple new sort of device types because of the frequencies involved. So you can imagine at those frequencies, the PA and kind of some of the beamforming happen in a singular device. So there's a device called a beamformer, which is effectively a multi-channel PA. So you've got a single input, a bunch of phase shifters, several output stage PAs, and that integrated device is a beamformer. So that's another example type of amplifier device used in some of the base stations and handsets for millimeter wave.
Is that something new? Because there's been a lot of talk over the years of how to do beamforming in terms of analog, digital, hybrid. These kind of new devices, are they tending to go more towards digital, or are they still more of a hybrid design?
That's a really good question. So it's not entirely new technology. I mean, the defense industry has been doing beamforming with like ESA arrays for decades at this point. Mm-hmm. And but it's really new to the wireless world because that becomes extremely important at millimeter wave because of some of the frequencies involved. I think it's a particularly interesting technology because part of the challenge of introducing it in the wireless world is you have to make it a lot more power efficient, scalable, cost effective, reasonably small in footprint. So it's somewhat of a different challenge for the wireless industry.
I'm hearing a lot more about the PAs, and particularly the efficiency or lack thereof.
Yeah.
What kind of work is being done to improve that? Now that 5G works, we have to improve it.
Yep.
So, and one of the issues that I have been hearing a lot about is PA efficiency. So what's being done about that?
Yeah, so there's a lot of different techniques that various engineering groups are using to improve that. One of the most kind of classic techniques is envelope tracking, which obviously you're very familiar with. It was used pretty extensively on the 4G side when LTE first came out, and LTE kind of created this issue where when you got to the LTE waveform, which was an OFDM based waveform, you're getting the relatively high peak to average power ratios. And so it started in the base station, and then eventually in the handset, you saw a number of companies using envelope tracking, which is a technique to basically modulate the supply voltage of feeding into the PA so that you're operating the PA at the compression point a larger percentage of the time. And that was primarily done with analog circuitry, where you have a detector detecting the RF and then modulating the analog. And it has some limitations in terms of the bandwidth supported. The most LTE waveforms in the uplink were no more than 20 megahertz wide. And so when you started moving to 5G and some of the 100 gigahertz or more in the uplink signal bandwidths, and then upwards of 800 megahertz in the downlink, that technique wasn't really efficient. So we've done some work with a company called ETA Wireless on a digital envelope tracking technique, where they're developing that technique and obviously selling it to their customers. And we've really partnered with them on the testing side to make sure that they're able to do that successfully.
Can you tell me how those devices work?
Well, there's a couple different, and I guess there's a couple different techniques that ETA Wireless has done. One of those is there's a technique called asymmetric multi-level outphasing, which is some work that that was done as a part of a research project at MIT, and that's one technique where you actually take the waveform itself and you break it into multiple streams, and then use multiple PAs simultaneously to generate that signal. So you can imagine, if you think about how I and Q are 180 degrees out of phase, but then by doing an amplitude modulation of each one of those, you can add them together and produce a phase in amplitude modulation. In a similar way, you can take a waveform, and rather than try to amplitude modulate it, you phase modulate it in a way that the amplitude remains relatively constant through each one of those PAs. And if you think about it from an old RF point of view, if you think about the Doherty PA is an example where you have two discrete PAs that then go to a combiner. And there's benefits of doing the Doherty PA for that reason. Well, in a similar way, you literally have two discrete or multiple discrete PAs simultaneously amplifying a signal, which by decomposing the signal into two parts, you can get a lower peak to average ratio at each of those PAs, which means that they're operating at a higher efficiency. And then when you combine it, you get an overall aggregated efficiency. So that's actually one of the first types of technologies that ETA is used to improve efficiency. Now, of course, they're moving into other digital envelope tracking techniques as well, where it's similar to the analog technique, but you're doing a lot of those computations in software.
What is NI's involvement with ETA?
So we're primarily providing test equipment. So we've worked pretty closely with their engineering team because of the type of research that they're doing. There's a lot of unique measurements that they want to be able to do. There's a lot of really unique synchronization challenges between some of the RF and the digital interfaces in order to get that to work.
What kind of measurements are they trying to do?
Usually you're testing things like, obviously you're testing the DC power consumption, voltage, power, current consumption. And then on the RF side, you're looking at things like EVM or adjacent channel power. So those are from an RF and 5G device point of view, probably the two most important figures of merit. Because anytime you do some sort of distortion to some of the baseband supply to a signal, or anytime you're doing anything to distort the signal path, you can create distortion, and that'll show up as an EVM result or an ACP distortion. So those are the primary measurements. And those measurements are actually being doing at millimeter wave to support the frequency range 2 bands of 5G.
Does the equipment, especially at millimeter wave, does the equipment use an IF to bring the frequency down, or does it digitize directly in the RF?
That's a good question. So our design for the millimeter wave instrument actually uses a couple different frequency conversion stages. So the way that we've designed it, and you're kind of alluding to this, at millimeter wave, you have the insertion loss can be pretty high as you cable out over any length of trace between the device under test and the instrument itself. So what we've done is we've designed our instrument in a way where we have a millimeter wave head design. So you can think about our instrument as broken into pieces, where there's a base unit, which is basically an IF instrument, and then a millimeter wave radio head. And then if you have your device under test on a desk, for example, you actually can put your radio heads, your millimeter radio heads, right next to the unit itself. And that minimizes your propagation loss or the insertion loss between the device and the head. And then that head actually down converts to an IF signal that's around 10 gigahertz. And that's a much more manageable way to bring that signal back into the instrument, because not only is the IF signal and trace length calibrated, because we can control that calibration plane, but it's also at a signal where you can minimize losses and then the resulting SNR loss that you get in the instrument itself.
What do you see going forward in terms of other devices that are coming down the pipe, you might say, that will need testing? What kind of new devices are you starting to see?
Yeah, so probably one of the biggest examples is the antenna and package technology for millimeter wave. So even the infrastructure chip makers are looking at that now, because it's really a cost and footprint point of view. But if you think back 10 years ago, like the idea of doing an over-the-air test and production test was just absurd. You wouldn't do it because you couldn't control some of the signal path characteristics and the propagation over free space. But when you get to a device where you take like a millimeter wave beamformer, you integrate the antenna into the package itself, you get to the point where literally the only way to access that signal is through an antenna interface. And so one of the kind of the next frontiers of 5G testing is being able to figure out over-the-air testing, both in the validation lab, which I think is well understood, and in production. And in the lab situation today, I mean, we have a pretty compelling solution where we use an anechoic chamber, and we have a compact antenna range with a reflector. So you get a relatively small footprint chamber to do, millimeter wave testing at 28 gigahertz and so forth. But that's not really a scalable solution in production tests. So the next kind of evolution is trying to figure out how to be able to successfully test that sort of device in a production test environment.
So far, 5G has been about cell phones. And as the infrastructure builds out, I know that release 16 is complete. So we're going to be starting to move into other devices. What kind of devices have you heard seem to be coming down the pipe? And what kind of challenges are those going to bring to engineers that are different than doing cell phones? Because cell phones, there are X number of manufacturers. You start getting into many devices, you're going to have a lot of people who may not be RF engineers now suddenly having to deal with this RF. So what kind of devices do you see coming next with release 16?
Yeah, that's a good question. And I think, it's important to keep in mind in the timeline of sort of 5G deployment, we're still pretty early. And so even from what's getting rolled out from an infrastructure perspective, it's still very much, enhanced mobile broadband, base stations, high volume, high throughput devices. Millimeter wave isn't really even rolling out in mass yet. So that's, probably another topic. So we're still very early on. I think on the beyond that, a lot of the types of devices that you see are really, I think some of the next ones are really automotive. There's a lot of work being done in the 5G V2X standard in order for vehicle-to-vehicle communication that actually started in LTE with LTE Direct, where a lot of people don't realize this. It's actually officially supported in LTE, where two radios can actually talk to each other without talking to a base station. It's part of LTE Direct mode, which obviously the carriers don't like that necessarily because, I guess it doesn't require a base station when you do that. And so I think that's probably one of the most obvious examples where there's a really strong need. And then beyond that, I think we have a lot of work to do on the power consumption to make some of the mass IoT devices sort of work. I think from a power efficiency point of view, we haven't really hit the point of having ultra low cost radios where you could put a radio in operating on a battery for 10 years. So there's still a lot of work to do in the engineering side to make that really usable.
Well, so far what we've seen is that heat is a problem with 5G, especially at millimeter wave. David, thank you very much for your time. I appreciate it.